Hello, my friends. Welcome back. This is Dr. Mohamed Nezami coming to you from Jerash, Jordan, Pompeii of the East, Roman Jerash. We had a good summer and we are resuming back our video series on the design and development of high frequency and high speed circuits. So, ladies and gentlemen, as you might know that I have this, let me just get this tiny here so we can, this is my YouTube channel on the web. And this is my LinkedIn profile. I welcome you to um, see the video. um, uh, some of the videos. I have various videos and tutorials on electronic, high frequency microwave electronic designs. And this summer, I resumed a little bit vacation, but I'm back and we're going to start a new series. Today's series basically is going to be on the design and development of optical front-end receivers. And this is part one. Um, this is on electro-optical front ends for optical sensors. And we'll start today with the first simple part. And then we get more involved as we go in the coming month. So, just a little advertisement. Basically, I'm an RF analog design consultant. If you have any need for design services, I have a very rapid development scheme where I take your requirements, your specifications, and what I do is I work with you, and sometimes in weeks, months, a month at most, in most of the cases, I will produce to you a BCB, fab files, and I will work with your engineers, technicians, and test engineers, system managers, on producing a workable prototype, and then I follow up with you on modifications or whatever. If you have a design that has obsolete parts on it, I have a specialty in that. I take your design files, be it in Cadence or Altium, and then what I will do is I will update the parts that are obsolescence. And I work very inexpensive because I work out of Jerash, Jordan, unlike expensive places like the US and Western Europe. You can reach out to me via this phone here, and it's connected. I've got WhatsApp hooked up on it, so you can, or via email. And my email is scattered all over the net. Just type my name, it'll come up, and you can go to my LinkedIn account and also get that. So let's get back to our first session in this season, which is on the design and development of optical front-end receivers with high-speed circuitry. Basically, optical devices really that I'm interested in here are basically made of optical diodes, okay, and the silicon photomultipliers. And basically, these are be it laser diodes or IR diodes, visual light diodes, photodiodes of all sorts, and the photomultipliers. These are devices that goes into many industrial systems and products. And they can vary anywhere from defense applications to commercial to consumer to medical And I've listed some of these stuff in here, like for instance, in fiber optic communications, when you have fiber line and on either end, one of the ends, you still have to receive the signal, which is optical, and convert it to electrical, and that's basically what I'm interested in detailing here. Data storage, as you know, CD drives and so on. In medical treatment and medical imaging, as you know, that's also a common area. And industrial process, cutting, welding, and so forth. Consumer electronics, like, barcode scanners, for instance, or distance measurements, laser pointers, whatever. Security applications, which I probably didn't list in here, but it goes into consumer electronics. And then into automobile safety, mainly like, laser radar nowadays. That's becoming, or which is LIDAR, is a common application. And in defense and aerospace, basically, in imaging and target sensing, target tracking, and so forth. All right. Now, if you just a quick overview of optical devices, they can vary anywhere from with fiber optic attached, avalanche and pin diode, laser pin diodes, photodiodes, silicon photomultipliers, and so forth. And you can see these devices all over the electronic industry being applied nowadays. So what's a an optical front end system? Basically, a receiver. Basically, we've got two words. We've got the digital word represented by analog to digital converter, and we've got the physical word in here, which is basically your optical device. That's your optical sensor. And and in between now, this signal comes in weak light or visible or invisible laser. And then what we have to do, we have to convert that light, of course, to first of all, to we have to detect the current that goes through this semiconductor device in here. And then what we do that was nowadays, as you know, with the transimpedance amplifier, which is really an amplifier that converts current to voltage, basically, and it has a gain that is in terms of resistance, because you're really your input is current and your output is voltage. So you take the output voltage to the input current. That's really resistance, and that's where the name transimpedance comes in, because you're really transforming the current sensed into an impedance into a voltage. Okay. And then, of course, we have the stages where we have to take the signal. It's really weak first. We amplify it a little bit with minimal noise additions to it. So the signal to noise ratio is preserved. And then we go through some kind of multi-stage of filtering and level shifting, you might say, analog level shifting, to try to get the signal up so that you can actually view it within the dynamic range of the analog digital converter. And of course, we got a reference, a voltage reference that is common to the ADD and to all of these portions in here. So we take a reference, and that reference we try to track, because of the temperature variations. We try to commonize it between all of these so that we can say. Now, the issues that are involved in an optical front end receiver, basically, we've got as far as the sensor, we're concerned with optical power, how much optical power is falling on that lens or on that diode, and then the current through it that gets induced, okay, and the signal bandwidth, the information bandwidth, okay, and then of course the noise, okay. So we're battling to preserve the maximize the signal while keeping the noise at a controlled level. And then, of course, the on the other side, the ADD is the one that really represents takes this analog signal or optical signal, which has been converted to an electrical signal. It digitizes it and represents it numerically and stores it in memory for further processing. And in that sense, what we're concerned with in the ADD is really what is the full scale power of this ADD, because we really have to take a signal that is in nanometers or microamps, nanoamps or microamps. We have to convert it to a level where we can see it in the ADD dynamic range. And ADD's dynamic range is usually is contained between two boundaries. You've got the quantization noise of the ADD, okay, which is the minimum that it can really, if you terminate the input, what voltage, what numerical value do you get? And then, of course, the saturation level, which is the all ones case in this case, which is what we call full scale. And that's usually really represented by the reference voltage. So it's between your ground and your reference voltage, which is in this case it could be 3 volts or 5 volts. So and that's why this intermediate stage in here is very critical because we really have to. It wouldn't do you any good if you try to build a real nice front end receiver, and then you end up coming in here and chopping one-fourth of it or only utilizing 20% of the dynamic range of ADD. You really want the digital signal to noise ratio complement the analog signal to noise ratio. Okay. And of course, in the middle, these stages in here, what we're dealing with, we have a chain signal gain, we have the chain added noise, and we have the chain noise bandwidth, okay, and information bandwidth as well. So let's go in. And so what we're going to do is I'm going to start out with just basically looking at this piece here today in a introductory level. And then we're going to further until we get to work with the whole thing in here. So, meaning try to design this front end completely from A to D to the sensor. So, but today we're going to focus on transimpedance amplifier, which is the first portion of this. Now, the trans impedance amplifier, like I said, we've got a diode, okay, that is either negatively biased, positively biased, okay, either way it could work. And what we do is we hook it into a high-speed amplifier, a high-speed operational amplifier in this case. That's another thing I forgot to mention. When we're dealing with these amplifiers, they're really nowadays, because their information bandwidth is in the gigahertz. Um, we're really dealing with the radio frequency circuitry here. So, and that brings to mind the amplifier, RF radio amplifier design, low noise amplifier design, which means, Smith chart, which means matching the gamma noise, which means using S parameters to design this thing, and large signal modeling and all that, which, by the way, if you go to my channel, I do have some of these, many of these, like in this case, here's one here where we're designing a low noise amplifier K, KU and KA band. But in this case, this work has emanated from analog work. So even though these devices are in the few gigahertz nowadays, we're really still designing them based on analog approach. And that's what I'm going to do today. However, that doesn't mean that you can't design this using conventional as an RF design, which I will get to in a moment. So we have this, and then we go in, and all we have is that we have a feedback resistor in here on this op amp, high speed op amp, okay, which has a gain bandwidth product somewhere 5 gigahertz, 8 gigahertz. And then we have a little capacitor in here, some picofarads. And what this does is that the current that gets induced in here goes in here. Of course, it can't go into the op amp, the inverting port, and it goes through and it creates a voltage drop across this resistor. Okay, And of course, the output simply in here is really the output voltage in here because no current goes in here, no current goes in here. It's only this resistor. It's really this current times the value of this resistor, the feedback resistor. That's how it is, but very simple. Okay. So, but in actuality, there is more to it. Okay. First of all, this op amp in here has a is a closed loop system, and if you have you will have parasitic capacitances in the package, the optical package in here, and in the amplifier device, where the system becomes unstable unless you use some kind of capacitor, feedback capacitor in here. What this does in here, it limits the gain at a certain portion of the frequency where the gain just flies out of the roof and this thing oscillates. So if you ever built a transimpedance amplifier, the first thing you will see is that it will oscillate, most likely, because unless, of course, it was designed really well. Okay, and that's what we're trying to. That's what I'm going to try to introduce today. So, okay, let's go further. Now, this op amp in here, of course, there are two ways to configure this op amp. Either as a an inverting non-inverting one, or as an inverting one. So, which means really you have a 180 degrees phase shift. In our transimpedance amplifier, really, it doesn't matter because when you have an ADD here, okay, really everything is digital. So you just flip the most significant bit, and that flips everything back to where it should. So digitally in the digital domain, we're really, but still though, we have to treat this in such a way so that we have to keep track of where we are in terms of the DC offset or the reference voltage in here in this case, okay, and in terms of the polarity, so that when we come here, we know where we are in relative to the full scale boundary of this ADD. Okay, so we could either have non-inverting where signal goes in here, and of course your gain is really that's a conventional gain. If you build a Kirchhoff's current law in here, you can see that the gain, the V out versus Vn, is really according to this equation, which that's you learn that in first year college of electrical engineering. Of course, you take the ratio of these and you add one, and that's your voltage gain. Or it could be an inverting one where the input in here instead of being in here and then non-inverting. And in that case, of course, the gain is has a minus sign or 180 degrees phase shift. And it's just basically the ratio of these two here. Okay? So just so that. Now, furthermore, the transimpedance amplifiers really, most cases, you take an amplifier and you feed it with both voltage rails, the positive and the negative uh, supplies. So now what you really have is you have your 0 volt in the middle, and you have above zero, 3.3 volts, and below that zero to down to minus 3.3 volt. And that signal, you can control the gain so that that signal can be located anywhere in there. But it has to be symmetrical around zero because this port here, the non-inverting port, is zero. And we could have it this way, or you could have it where the diode is actually back reversed voltage. And the back reverse voltage avalanche or pin diodes, we have a certain need for that sometimes, and it's beyond the scope of this session. We'll talk about it maybe in the next coming sessions. But this is really the simplest form of a transimpedance amplifier, single stage, of course. Now, in addition to this, now, assuming that you don't have negative voltage to provide to your op amp, then you can go as a unipolar power supply device where it's powered from positive and the other one is negative. And in that case, of course, if you have this at ground level in here, what will happen is that the negative voltages of the waveform, the below zero, they will be chopped off basically. You won't see them. So one way to circumvent this is that we bring in a DC offset to lift your 0 point above at a certain DC value, which really didn't do anything. All it does is that now I can see the full signal that comes in here, both the positive and negative. Okay. And of course, in the chain in here, you just keep track of that. And you either remove that at some point or keep it until you come in here where the ADD really is always from quantization to full scale, and that's positive basically. So you would DC level shift it, and I will talk about this in the next sessions basically. So the transimpedance amplifier in principle is very simple. It's just basically we've got the diode, the optical device in here, which produces current. Okay, the current goes into the input of the high speed op amp, and because really this is a high impedance point in here, there's no current goes in here, so your output is basically the current completely. The current that comes into the device, it goes completely out. And what happened is you can build a Kirchhoff. This voltage here is zero because this is grounded. So you could take the zero here minus V out, divide by RF, that's this current. And then you've got this input current. And so this input current is really equal to this current in here. And this current in here is this equation in here, which is this VDEV here minus V out divided by that resistor. And you get this equation here. Of course, this is zero because this is grounded. Okay. And then you end up with this. And then if you solve for V out, it turns out to be this. And that's your transimpedance gain, okay, which is basically volts per amps, really the unit of this, okay? Now, that's really in simple form. This is very plain, simple um, transimpedance amplifier. But in reality, you've got the photodiode in here or laser diode in here, and you've got the feedback network is shunted with this cab, which limits the bandwidth of this so that you wouldn't oscillate. And this one here creates a pole. If you take the transfer function of this here, if you solve the transfer function, which is V out versus I S, in this case, I use this as the source current. You end up with this equation here, and this is from where the impedance, the parallel impedance of this really is the 1 over SCF Laplace transform, and then RF. These are in parallel. So when you solve that in here, you end up with this equation here. This has no zeros on top, and then a single pole that is controlled by the capacitance and the resistance, the feedback capacitance, feedback resistance, which is this. Now, with this equation here, you really can control at what frequency, okay, you would want this op amp to start cutting off, okay, because this is just a first order low pass filter becomes, okay. So in essence, what this will have, it'll have a flat and then it will fall off because of the zero in here. Now, this, of course, ignores any parasitic capacitance with the associated with your diode and with your amplifier and the layout, the way you do the layout on the BC board. In actuality, what really will happen is you will have CD in here, which is the parasitic capacitance. That is an overall summation of the capacitances, parasitic capacitances that are associated with the input of the op-amp device and the laser diode. Okay, so if you sum them all and represent them with a single one in here, and it's beyond the scope to talk about the modeling of this diode really, but this diode we represent it just simply by a parallel resistance, which is high. This is like hundreds of mega ohms, and then a capacitance. Okay, if you do this and solve for the transfer function of this, you really end up with this formation in here, which now incorporates a zero at, as you can see, a zero that is controlled by these two, the summation of the feedback capacitor and the parasitic capacitors. Okay? And so, having said that, now you have a zero that you come in here, and at some frequency, you have a zero that climbs up. So, meaning your gain starts increasing as you go higher in frequency. And of course, you have the slope of your up amp and the feedback zero pole, which is this one in here, due to this one. And these will meet at some point and cancel each other, and you end up with just basically sort of like a flat region. Okay. And so this is now this capacitor in here plays a big role because it will create instability for this system. And that's why the oscillation comes up. So if you drop CF, it will basically it will have a zero at some frequency and it will oscillate. I'll show you in a minute. In the coming sessions, I will have a whole video on this. So just sit back and keep this in mind, and you will see in the one of the sessions how we treat this, how we design this based on uh, Okay, so let's start doing some examples. Since we have this simple circuit in here, so we can throw this onto one of the analog simulators, SPICE programs, and start looking at how this works and how the oscillation take place and so forth. So I'm going to start out with picking a device, which is this device, OPA 858 from Texas Instruments. And this device is pretty nice. It has a gain bandwidth of 5 gigahertz, 5.5 gigahertz, and it has a very low parasitic capacitance. As you can see, the differential parasitic is zero point 0.2, and you got the common mode is 0.6, so that's 0.8. It has about a single picofarad on here, parasitic capacitance due to the diode, but you still have parasitic capacitance that is from the I'm sorry, 1 picofarad associated with this device, if you were using this device in here. So you still have the diode parasitic capacitance, so they add up, okay? So I'm going to take this and use it to build, just to visualize how the design of this. So the first thing is we put this device in here in the simulator, and this is I chose I could do this in the linear simulators from Spice Cadence, but I chose to do it with TI's Spice program, which is Tina. Okay, it's pretty simple to work with, and you can download it for free from their website. All right, so I'm going to put this device in here as I put it right here. Okay, so this is the amplifier in here. So as you can see here it is. Okay, so I'm gonna put this and I put in the negative 5 volts, the positive 5 volts. And in this case, I threw in a current source mimicking a photodiode. And I'm running a square wave with 10 megahertz right now with about a half milliamp. Okay. And I'll show you in a moment why I chose these values. And this here is 2 kilohertz. Okay. So theoretically, this current in here will flow in here and will come back here. And what you're going to get is your output voltage is really going to be the 2K times a half milliamp. So, which means it's going to have 1 volt peak to 1 volt peak, plus minus 1 volt in here. So, and so we solve this and we get 1 volt, of course. And your current source in here is square wave that has positive, which is 1 volt, and negative 1 volt at 10 megahertz. So you end up with plus minus one square wave at the output in here. And when we run this, of course, now the first thing that will hit you, is you look at the DC transfer function. It works out beautifully, of course. You can see that the system has a range of current where it's linear, and then above and below, you basically saturate to the rails, the 5 volts. In this case, you can't reach 5 volts. You go to 4.3 maybe volts because of the headroom on the internal circuitry of the op amp. And if you look at the frequency response of this, you can see that the gain as a function of frequency peaks out. First of all, it goes all the way up to like 3 gigahertz. But then it does peak out, this gain peaking in here. And whenever you see a closed loop transfer function that does this, you know that it's going to oscillate basically, because you got about 80 dB ohm um, gain. And that's what will happen is you come in, here's your current source. That's the current source in here, which oscillates between half milliamp to negative milliamp. Okay, but alternates back and forth. And what will happen is your output will alternate right at 1 ± 1 volt, according to this equation here, but it will be accompanied by this oscillation. And that's basically ruined your signal. So if you're trying to detect on-off optical power, this is what you end up with. And just to show you, so we've got this here. And first thing is we want to do is if you check the transfer function with these conditions in here, as you can see that this is your closed loop gain and the phase, and you can see that you know your system has about 80 dB of gain at the peak in here, which is unacceptable. We want this gain in here, which is about 65 dB or so. Okay. So, and now if you, let's say, like I said, we set this at a square wave that is at half milliamp or 500 microamp with 10 megahertz. Okay. And what will happen now if we look at the transient response of this and look at 300 nanoseconds out of this, and this is basically what we end up with. And you can see that, you know, this is the 1 volt is right here, so it's oscillating back and forth between -1 and +1, but it's overshooting and oscillating, as you can see. And why is that happening is because this op amp in here really has internal parasitic caps in the model that are causing this. So to overcome this, basically what I do is I have a little capacitor in there, just add zero point 0.2 picofarad, just a small tiny cap. In some cases, this cap is not physical cap, but really it's a parasitic capacitance of this resistor in here. And automatically you can see that the signal has settled down with a little overshoot, but it has settled down. So now your input current on and off doesn't cause oscillations. But of course your AC response now has came down and it's pretty nice. And you can see that it doesn't have any gain peaking just by adding that there. So what does that happen is if you go back to the AC model in here, this is what's happened. Without that cap, this is the transfer function. You've got a single pole. Okay, no, I'm sorry. Without, um, sorry. Okay. Well, not yet. So let's just, there's more to it. So let's keep it to that point. So in any case, um, that's what will happen. Okay. And so if we go back to this, so let's see that that's this here. So we're gonna zoom and see this. So I added this cap in here, which is 200 femto. That's the value. Okay. And now same circuit, didn't change anything. So first thing you would want to see is you go to your AC response, and you can see that the response, there is no gain peaking, okay? And you can go all the way to 2 gigahertz and you still have 50 dB of gain. And it behaves really well. And if you excite it with the same current source, basically you get this. Let's see, let's view this separately. So I've got on off, this is the current, the I current, that's 50, between plus 500 microamps to minus 500 microamps. what happens, and you get a nice voltage at plus minus one with a little bit of an overshoot. Now, if you don't want this at all, of course, at the expense of the bandwidth, you would want to increase this. So let's say I increase it to 300 femto, which is zero point 0.3 picofarad, and rerun it. And you can see that now you can see your output doesn't have any overshoots, which is desirable. But of course, really, like I said, that's at the expense of narrower frequency. So now your bandwidth, as you can see, you have went down, and you can see that the gain right now is limited, way limited, at lower than the other case. Okay, so now having said this, so let's see how do we design this. So I did now, how did I pick these resistor values in here? 2K. Obviously, it really 2K determines the output voltage in here. Okay. So, but we have some equations, some simple equations that uh, basically determines the value of this cap and the value of this resistor, which determines the 3 dB bandwidth of the transimpedance amplifier and the overall gain and voltage swing. Just as an, let's do this through an example. Okay, so basically, you go back to this equation here. Okay, this equation here, and you know that uh, of course, if the frequency is zero in here, you got minus IS times RF, and that's basically the output voltage. Okay, so that's the first thing that says is that your output voltage requirements is determined by the feedback resistor. Okay, now when you have frequency in here, okay, that you can see that the gain is determined where the gain value is located at the regions before some kind of cutoff that starts eating out your frequent gain due to this pole in here. So you can actually determine what value is that. Okay, so and that's what we're going to do in here. And this is really fundamental electronics. So what we have now is we have the frequency that controls where this thing in here will almost short that resistor and give you no more gain. It's controlled by 1 over 2 pi RC, which is, first year electronics, basically. So first thing is, let's do a silicon pin diode with that has a responsivity of 0.5 amps per watt. Okay, this is an example. So I'm going to try to show you. Giving a photo, an optical diode. How do you determine these values in here? And then saying I have a 1 milliwatt of optical power falling onto this. Okay, and then the bandwidth desired is 300 megahertz. Okay. Now, the diode parasitics in here, I assumed is 10 picofarad, which is a little bit high value, but that's because a lot of these diodes that you might use are like these leaded diodes, and these will have a lot of parasitics on them associated with them. Okay. And then let's say that the desired voltage out of this here, okay, which I'm assuming that I have a front end here that doesn't have this, that only has a single stage device that wants to go to the ADD, that I wanted to say 1 volt peak, okay? So design these values, the CF and the RF, and that's really easy. The first thing I want to do, how much current, peak current, do I get from this diode that has a responsibility, which is this is a spec of this diode, which is its ability, how much its capabilities of giving amps per watt, per optical watt power, is determined by this. So we have 0.5 amp per watt. That's the output in here. And then I have the output power, which was given to me, which is 1 milliwatt. So if you take the 1 milliwatt in here and put it in this spec in here, you can actually determine the current. And in this case, you do this ID is basically zero point 0.5 times 1 milliwatt, and that gives point half a milliamp. Okay, so a half milliamp out of this diode will be produced when it's exposed when its exposure is to 1 milliwatt of optical power. Okay. And having said that, then now I want also 1 volt peak in here. So, which means that this current, when it goes into that resistor, I want it to give 1 volt. So therefore, I can determine what that resistor is. And you do that simply by saying 1 volt is equal half amp time that resistance. And that means your resistor in here has to be 2 kilo ohms, 2000 ohms. Now, the other parameter, which is basically the capacitance, this capacitance, and the value of this capacitance, of course, this really is, you can't pick any capacitance, really. It has to fulfill the stability requirements. It has to produce in conjunction with the parasitic capacitance in here, it has to produce a transfer function which has from control theories, you might know second order control theory modeling, it has to have a 40 degree of phase margin at the 0 dB gain. And so that itself is another topic which we will look at later on. But for right now, let's just say that this here, we wanted just a way to control the frequency response of this TIA. So meaning, give me what value of that capacitor that will cut off at 300 megahertz. Okay, so this is 300 megahertz. So I plug it into this equation here. Okay, and then I get 0.27 picofarads. Okay. So, and I do this, so we've got the TI device in here. So if you do that, put 10 picofarads in here, put the 270 femtofarad, which is the 0.27 picofarad, and the 2K in here, and let's see what this circuit does. Theoretically, the VF1 here, it should be really is a half amp, which comes in here, multiplied by 2K is the output voltage, which really is 2K times zero point 0.5 milliamp, and that's 1 volt. And if it's negative, because this is an AC current, we should get minus 1 volt because it's just the reverse sign. And when I do this, this is exactly what I get at 10 megahertz. Okay, at 300 mega. I don't know if this was run. I'll see in a minute. Okay, and the frequency response, of course, it does have a little bit of peaking, but it still did not complete oscillation. It's critically damped, we call this. And this is might be for some people that might be acceptable, for some might not. So, and of course the DC bias transfer function is well controlled. So, okay. So let's look at that. And so that's basically this circuit. So okay, so basically I have this. Let me zoom further. Okay, so I've got 270 femtofarads. And this here, let me just see what the frequency I run it at right now. It's still running at 10 megahertz, so we'll see in a minute. So if I run this, okay, right now, so first thing is, if you look at the transfer function of this, including the 10 picofarads in here, of course, the parasitic one. And this is basically what I get. So you can see that at gigahertz, it's way down. So it's somewhere, if you were to measure up to this point here, 3 dB bandwidth, 100, 200, 300 megahertz. So right here, which might be correct. Okay. And so now let's just look at this. As you, this, of course, like I said, so this works, but now let's increase this to say like 100 megahertz, and this might be not acceptable. So let's see of course, AC wise, it doesn't change anything because that's just a source of driving. So the gain frequency response doesn't change. But if you look at the transient, okay, now it's going to be different. So now you can see that it actually it didn't oscillate, but you can see the frequency response has changed. It's too slow. Okay, so which means we have to widen the bandwidth of this. All right. So this really shows how, in principle, you design this as a starting point. Okay. So basically, here I put these so that we can play with the model a little bit. So we want to show the parasitic effects and impact on feedback capacitor. We need to show the unipolar versus bipolar voltage rail, show removal of gain, peaking, and oscillations, and show clippings. Okay. Let's postpone this a little bit, but let's look at something else now. Now, like I said in before, this circuit in here, while it works well, in some cases I can't have a negative supply. I can't have a negative power supply. And if you put in zero in here, okay, that will basically clip some of the signal. Okay, so and that's what. So in that case, what we want to do is we want to add some little DC offset. And that's what this circuit does. So basically, we bring in the 5 volts and the device in here, and I'm still the same device. I just changed this was grabbed from a source that used this op amp, but forget that. So I've got the power supply is 5 volts and it's grounded on the negative. But I'm going to insert a DC offset at the non-inverting port, which is 5 volts divided down by 2 resistors and bypassed real well, okay, to a certain voltage value, which is, I'm going to call it V reference in here. And that is the reason for this is I want to pull this up because I can't have this signal swing into the negative because there is no negative for this op amp to operate on. There is no negative real. Okay, so now in this case in here, and the rest is still the same circuit. Okay, so what will happen in this in here is that you still have this portion of the signal that is this, and that's, let's go back and remind you of this. Uh, so I still have this circuit in here, which is the V out is controlled by this, okay, which is an inverting op amp. But what I have now is I have to add a positive value because what I do is I take this signal in here, which is this here, okay, that caused this here at the output, and then I have to add to it a certain voltage in here that's controlled by that voltage resistor divider in here. So we got 5 volts, which is this, divided down, and then I add to it this current in here, the voltage induced in here, and that will pull this so that it's not anymore in the negatives, okay? And that's what I did. So let's look at the circuit. So I took the circuit, and all I did is I added a 3K, 2K value. So that means this 5 volts gets divided by 3 and 2K divider, which means this point in here is 3 volts DC. So now the output is always going to have, when you don't have current even, it's going to have 3 volts in here, okay? And so in that case, then now the VF1 in here is really going to be the 2K times this current, okay, here, plus 3 volts. But of course, this one here really varies between 0.5 milliamp and negative 5 milliamp. So in that case, this one here will be either a 1 volt peak or negative 1 volt peak. Okay. And if you add, in either case, if you add those to 3, you get, at this point, you get 4 volts. At this point, you get 2 volts. So which means that the AC signal that is induced by this photo device in here between, which is the current in here, which is from negative a half milliamp to positive 5 milliamp square wave in this case, I'm just stimulating, is going to produce a voltage square wave between 2 and 4 volts. And now, therefore, I don't have an issue with this signal being real to positive rail to negative rail. And so I do this. The AC response, of course, before this was before when this was grounded, AC wise, nothing changes. Okay. And then DC wise, nothing changes because but if you look at the output now, the output varies between 2 volt and 4 volts. And it still has the same thing like this does, except now what will happen because this one here went to 4 volts is going to clip because this thing, the op amp itself, may not uh, be able to produce. And that's what you see in here. You can see that there is a little clipping on this. And so therefore, meaning the 3 volt that I put this at in the middle of the reference voltage may not be appropriate because you're not really seeing the full dynamic of the signal. So, and let's look at that. Okay. So basically, where is that circuit? Okay, so this is this circuit. So I added, this is if you, let's see, run the DC calculate node voltages. Okay, so if I come in here just to test, this here gives me 5 volts, the probe in here. And if I come in here, this is 3 volts. Okay, so you can see this is working. Now, AC wise, nothing changes really. If I come in here and you look at the AC transfer function, nothing changes. So I still have my AC response the same. But look at the transient now, which is the AC signal. And now what happened is, as you can see, look at this. So if you look at this, this went from, this is basically 4 volts. And if you move this down here, this is 2 volts from 2 to 4. And look what happened here. So what you could do is you could, if that doesn't make you happy, is I could let's see, if I reduce this to say instead of 3K, this is let's say 2K. Make it reduce that voltage to 2.5 volts. Okay, let's see what that does to the okay, now you can see that we captured the full dynamic range, except we still really so you can see that now, but still clips. Okay, and the clipping is happening where that uh, op amp doesn't anymore, uh, and that's at 4 volts exactly. Okay, so we need to go lower than this. So maybe we can go to the, let's say, 1.5. Okay. And let's see, transients. Okay, so now we have no clipping anymore. So you can see that the signal is full because I reduced the DC reference in here so you can see that in the final stages of the of our optical receiver in here, we really have for the A to D, this is going to be critical how we center the the middle of the symmetry of the signal in here if it is periodical in that case. Okay, so all right, so now let's get back to this. Okay, so now but in our case, even though I says in this one in here, for the example that I did in here, I assume that it has a zero point 0.5 milliamp power signal in here, but in a lot of cases, it's really in the microamps or nanoamps in real life. So what you end up with, you end up having to really get mega ohm um, volt per amp in here. Okay, which means if you do that from the simple expression of gain bandwidth product, that means you have a huge gain, and therefore you narrow the bandwidth heavily. And we really don't want that. So the alternative way to do this is to do multiple stages so that you can use a TI first of stages, and then you can cascade it with just a volt per volt gain stages until you get a number of them, until you get to pass the signal within the dynamic range of the ADD. And so that leads to the multi-stage amplifier design. And that's basically, so what I'm going to do, I'm going to take this here and I'm going to cascade it with another stage. And that's what I did here. So I took the same op amp, high-speed op amp, put it in here and put just 10, a gain of 10 in this one here. Okay. So in that case, then the design of this is really simple. We still talk about the this voltage in here is the current times this resistor in here, which means it's for in my case, I went and changed this now to 50 microamp instead of a half milliamp um, of, of optical current going through this. And if you do that, now that means this output in here is going to be plus minus 100 millivolt. Okay. And of course, 100 millivolts, that's not even drivable to ADD. We need to magnify this further because at 100 millivolts, these ADDs, depending on the resolution of bits, uh, even one, you might not be able to toggle 2 or 3 bits from the ADD with this amount of voltage. Um, so meaning now you have to really pull hard. So what I do is 10 times this is going to be basically going to take you to plus minus 1 volt using this inverting op amp in here. And the good thing is that this is inverting. So you're now as far as sign of the there is no 180 phase shift. So you're back on track. Now let's see. So this is still positive and negative to, this one in here because this is really grounded. Okay. And I added a resistor in here. That's basically because you really want to balance the impedance between this port and this port. So this port looking out is 50 and this port has to be 50 ohm in here. This doesn't impact your gain at all. So, and what will happen now is that the ADD will not be able to deal with this. You still need either to add a DC offset in here or add another stage of DC level shifting. And that we will talk about in the next sessions. Okay, so let's look at the circuit. If you look at the circuit, you can see that the difference between them, this is VF1, this output voltage in here, and output voltage in here. Okay, this is the gain equation. You can see the difference is 20 dB, and that's really because you got 10 times the voltage, and that's of course in power. That's 20 log of that, and that you get uh, the voltage 10 volt per volt is 20 volt 20 dB of power. And of course, the transfer function for the current, for both of them, you can see how hard this becomes at the final point. Okay. And your signal is basically going to be oscillating between plus and minus 100 millivolt for one of them, which is this here. So this is your TIA, which has volts per amp transfer function. But this is really a voltage gain, a power amplifier, meaning it has volts per volts because you're driving in with voltage rather than currents. And the other one is plus minus 1 volt. So let's look at that one. And that should be this one in here. So let's view the full power. Okay, so this is basically what I've got. I've got this in here, same thing. The current in here that I'm putting in is 50 microamps. Okay. So if we run this AC wise, we should get two transfer functions that corresponds to the first stage and the second stage, and that's what we get basically. And you can measure uh, the difference between them, 66 dB ohm and 86, 20 dB difference. And now if you look at the transient of this, and you can see that this signal, there's two signals in there. This one in here, which is VF1, and this is the other one, which is VF2. So you can see here's the 180 phase shift between this and the input. And now again, this goes through the second stage and gets back to in phase with the input. And nothing changes except the voltage level. You can see that from this is here at 100 millivolt. Okay. And then if we go in here, okay, let me just let's take a second one. And that's 1 volt basically. Okay, so you can see that this is working well according to theory. Now, like I said again, really the principles are very simple with this. So, okay, so this really puts an end to the first session of the design of optical front-end receivers. Okay, so basically, which is this thing here. So now next, what I'm going to do is in the next videos is we're going to say, okay, now we have to bring in the A to D specifications and start looking at we're giving a dynamic range of a signal, okay, and a characteristic of the signal as far as bandwidth and the signal to noise ratio and so on. And we're going to look at the physical parameters of this optical device and try to somehow design this so that we can um, fully optimize the A to D dynamic range and then the chain in here. Okay. And that's basically going to be the topic of the next videos. Okay, ladies and gentlemen, so this is Mohamed Nezami again. I thank you very much for this opportunity and wish you a great day, night, wherever you are. Happy to be around the world. And like I said, please go ahead and go to my channel. I would appreciate if you go in and subscribe to the channel. That keeps me motivated somehow. Um, because as you can see, the more subscribers I get is the better. And that gives me feedback that to keep going. Okay, ladies and gentlemen, so thank you very much and have a great day, great night, wherever you are around the world. Thank you very much. Bye.